This lesson objective is students prove statements about segments and angles. So, in order to prove statements, we're going to use proofs. And what is a proof? A proof is a logical argument that shows a statement is true. A logical argument that shows a statement is true. So when we're doing proofs, we can use facts, definitions, properties, postulates, and proven theorems. We can use facts, definitions, properties, postulates, and proven theorems. So I've been saying since the start of the year, you need to memorize the stuff that we're learning here. And the reason you have to memorize it is you need to be able to use what you know to develop a proof. And if you don't have the information readily accessible in your brain, then it makes it a lot more difficult. So it's very important that you commit what we've done so far to memory. So a two-column proof is just one type of proof. It's where we use numbered statements and reasons. And they're in a logical order. So numbered statements and reasons in a logical order. Okay, so we've been doing if-then statements. When we do a two-column proof, you're going to see that we're given information and we're trying to prove something. And that's going to be where we start with our proof. Well, the given is the hypothesis of an if-then statement. So it's the if part. And what we're trying to prove is the conclusion of an if-then statement. In other words, the then part. So a theorem, we've talked about postulates before. What a theorem is a statement that can be proven. So you may recall that a postulate is a statement that is accepted as true without proof. So we don't have to prove postulates, but we do have to prove theorems. Okay, and again, remember another word for postulate is axiom, in case that shows up. Okay? So it's really important that you know the difference between a theorem and a postulate. All right. So when we're talking about congruence of segments, we can use reflexive, symmetric, and transitive when we're dealing with congruence of segments. So for instance, the reflexive property, segment AB is congruent to itself. So it's very similar to the property of equality, it's just now we're dealing with congruence. And so what you're going to do is you're going to put a little congruent sign after it when we're using the reflexive property of congruence. Symmetric, again, we're going to put our little congruent sign there, would look like if AB is congruent to CD, then they switch the order, CD is congruent to AB. Okay, and so we're talking about the actual things, the segments, and we're talking about congruent. So when we're talking about the segment, that's when you have to put the line over the AB. We're not talking about the length any longer, we're talking about the actual segment. And then finally the transitive property for congruence. If AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. This can also be used with angles, not just segments. So it's the same idea though. Reflexive property for congruence. When we have angles, you're just going to have angle A is congruent to angle A. In other words, angle A is looking at himself in the mirror. And for the symmetric property of congruence with angles, if angle A is congruent to angle B, then angle B is congruent to angle A. And then finally transitive. If angle A is congruent to angle B and angle B is congruent to angle C, then angle A is congruent to angle C. So the format for a two-column proof. When you do proofs, you need to have all the pieces. You need to write the given information, you need to write what you're trying to prove, and then you have two columns with your statements and your reasons. And you must draw any figure that is part of the given information. So it's important that you get in the habit of always doing this. On your homework, if you just write the statements and reasons, you're going to lose points. And you will definitely lose points on a quiz if you don't include the given and proof. So I want to know what you're given, I want to know what you're trying to prove, and I want to know exactly what figure they gave you. The picture should be on your paper. All right, so almost always we are going to start with the information that we were given. We were told that AC is equal to AB plus AB. That was given to us. Now, before we go any further though, let's take a look at what it is we're trying to prove. We were given that AC, the whole thing, is equal to AB plus AB. Well, I know by the segment addition postulate that AC has to equal AB plus BC. So the only way that AC could equal AB plus AB is if these two are in fact congruent. And so I'm going to use that, showing using the segment addition postulate and substitution to show that they would have to be equal to each other. So let me erase all this. All right, so we start off with what we're given. AC is equal to AB plus AB. Well, as I said, under the segment addition postulate, I know that AC would have to equal AB plus BC, because the two pieces add up to the whole thing. That is the segment addition postulate. So now if I look at this, I have AC here and AC here. And so what I can do is I can take what I have for AC right here and substitute it in right there. So that's what I'm going to do for my next step. Instead of writing the first AC, I'm going to write AB plus AB equals AB plus BC. So what did I do? I substituted. And now, if I what I'm trying to get to, okay, if you pay attention, where am I going? I am trying to prove that AB equals BC. Well, I've got an AB here and a BC here. So what do I need to get rid of to leave them alone? Well, I notice that there's AB and AB on both sides. So what I can do is I can subtract AB from both sides. And so if I subtract AB from both sides, I'm left with AB is equal to BC. And again, we used the subtraction property of equality to get there. So all a proof is really is a puzzle. How can I get from where I'm starting to where I want to finish? What logical progression can I make based on what I already know in geometry? We're going to do one more example of a proof. We are given that M is the midpoint of AB. And we're going to prove that 2 times AM is going to equal AB. Okay, well again, if you think about this logically, AB is equal to these two pieces added together, right? Well, if M is the midpoint, then because it's the midpoint, I know that those two have to be congruent to each other. And therefore, wherever MB is, I could put AM instead, because they're equal to each other because it's the midpoint. So that's the direction I'm going. So again, we're going to start off with the information we were given. That M is the midpoint. Of AB. And when they give you information, you have to stop and think, well, why would they give me that information? What is it that I can conclude because they gave me that information? What's it mean to be a midpoint? Well, what it means to be a midpoint is that the two pieces are equal to each other because it's exactly in the middle. So my next step is I'm going to say that AM is equal to MB. How did I know that? Well, that's what it means to be a midpoint. So if you find yourself saying, well, that's what it means to be a midpoint, or that's what it means for whatever situation, chances are it's a definition. In this case, the definition of a midpoint. So that's my reason. By the definition of a midpoint, I know that AM equals MB. All right, so what I'm trying to get to is AM and 2AM equal to AB. And so that'd be the same as AM plus AM equal to AB. Well, before I can get there, I know I can say AM plus MB is equal to AB because of the segment addition postulate. So that's where I'll go next. AM plus MB is equal to AB. And again, that's the segment addition postulate. The pieces add up to the whole thing. All right, so now, because I said that AM was equal to MB, where MB is, instead of writing MB, I can write AM. So to get from step 3 to step 4, what did I do? I put something in place of something else. That's substitution. All right, and now I'm almost there. I have 2 AMs on the left side of my equation. AM plus AM is just equal to 2 AM. And so I've proven what it is I want to prove. Your last statement should always be the thing that you're trying to prove. Now the reason for this, there's a couple of different ways you can look at it, and I would take any one of these. Technically, it is the distributive property in reverse. But I would also take, if you just put simplify, because essentially you're just combining like terms. So that's also something you'd write, is combine like terms. Any one of those would be fine for the fifth reason. A reason that you will never, ever, 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 ever have, a reason I never want to see, is prove. That is not a reason. That is what you're trying to do. So don't ever let me see that as a reason on one of your proofs. Never, ever, ever is that a reason. That's what you're doing. It's not a reason. Okay? So please never have that on your proof. All right, so that concludes this video. Thank you for watching.